Nothing you need to take notes on here. There's nothing I'm going to hold you accountable for. There's not going to be any problems on the test or in my math lab over this. I just want you to have an idea of where these weird new numbers called complex numbers come from. Where do numbers come from? Way back at the dawn of civilization, we decided we needed symbols to keep track of how many things we had. So we invented some numbers, and these weren't the original numbers. These are the symbols we use now. But we know what one thing is, two things are, three things, four things. So if we know we're supposed to have this many sheep, we can count. We know 1, 2, 3, 4. Yep, that's the right number. And then we started to do commerce, and we invented the concept of debt, right? Well, I owe you 6 sheep. I've only got 5 right now, so I'll give you the 5 that I've got. And now I have sort of -1 sheep, right? I don't have 0 sheep. I have 0 sheep, but I still owe you a sheep. So that's really different. And we had to invent negative numbers to keep track of our debts. And then we noticed that all these numbers are the same distance apart except for these two. There's a gap here. You don't go straight from having a sheep to owing a sheep. There's having 0 sheep in between there. So we invented a symbol for 0. And some people say that the symbol for 0, the symbol for nothing, is right there. To tell you it's right there, I'm going to put a circle around it. That's one probably BS story about where the symbol for 0 came from. As we started to get more sophisticated, we created mathematical operations: addition, subtraction, multiplication, division. And we decided that we wanted our number system to be what we call closed. We want every operation between two numbers to have a numeric answer. For example, if we add 3 and 5, we get 8. So if we take two numbers, 3 and 5, that are numbers that we have, the answer to one plus the other is another number that we have in our list. So we can add any two numbers on this number line. I was going to save the number line for later. But we know that we have our numbers on our number line here. And if you take any two of these and add them together, the result of that operation is also a number on the number line. 3 plus 5 is 8. 3 minus 5 would be -2. We get numbers on the number line. Same thing with subtraction, right? 3 minus 5 is equal to -2. So this list of numbers, which we call the integers, is closed under addition and subtraction. Because if you add or subtract any two of these numbers, you get another one of these numbers. It's also closed under multiplication, right? If you multiply any two numbers on this list, you'll get another number on the list. But along comes division, and we no longer have closure under division. If I divide 4 by 2, that's 2, that's on the list. But if I divide 4 by 3, I get a different number, which would be 4/3, which is a little bit bigger than 1. If I divide 5 by 2, I get 2.5, which would be there between the 2 and the 3. So we had to create new numbers in order to have closure under division. And the numbers we created are called rational numbers, ratio. Any number over another number is a ratio, and that's a rational number. And that's the definition of the rational numbers, is anything that can be expressed as one integer over another integer. And our rational numbers live in between our integers. Our integers are rational numbers, right? I can write 4 as 4/1, so it's a rational number. But there's all kinds of rational numbers in between these integers. And they're all in an order, right? We take any two rational numbers and we can say this one is greater than or less than the other. Then we've got closure under division, with one exception, right? We've got this 0 guy we're not allowed to divide by, but that's okay. We can have one exception to the rule. Then along comes square rooting. If we take the square root of any of these numbers, are we going to get another number on the list? The square root of 4 is 2. That's on there. What about the square root of 3, though? The square root of 3 is a number, 1.732, etc. It goes on forever, and we're not going to get into how to prove this, but it cannot be written as one integer over another integer. So he needed to invent new numbers in order to have closure under square roots. And the square root of 3 would be somewhere around here, 1.732. We've got the square root of 5 in here is a little bit less than 2.5, I think. The square root of 10 would be between 3 and 4, etc. Now these are called irrational numbers. And if we take all of the rational numbers and the irrational numbers and lump them together, we have our number line. We have, in order from least, we go to negative infinity, so it's really not least, to positive infinity. And every spot on this number line represents a number. Some of them are integers, some of them are rationals, some of them are irrationals, some of them are what we call transcendental numbers like pi and e. You may not have met e yet, I'm sure you met pi. And we've got all our numbers. And everything works beautifully except square roots of negative numbers. We still don't have closure under square root because we can't take the square root of negative numbers. So we need to invent another number. Notice I said we're inventing these, right? There's an old saying that nature or God, depending on who's saying the saying, invented the natural numbers, 1, 2, 3, 4, 5, etc. But all others were the work of man because we invented the concepts of negative numbers, the concepts of fractions, and the concepts of square roots in order to make our operations work well. So the only real numbers are 1, 2, 3, 4, etc. All the rest are fake made-up concepts by human beings. So some human beings said, we want to invent another number so that we can do the square roots of negative numbers. So what they said was, let's say we're going to define this new number as the square root of negative 1, and we're going to call it I. And there was a real controversy about it at the time. Half of the mathematical community wanted to do it, the other half didn't. There was this battle, and they finally said, okay, we'll let you do it as long as you call them imaginary numbers. So that's why we call them imaginary numbers, but they're no less real than any of the other numbers on this number line, with the exception of 1, 2, 3, 4, etc. Now, it's got a little bit of a different property here in that it does not live on the number line. We can't say that I is bigger than or smaller than 1 or 2 or 3 or anything like that. So it can't live on the number line. It's got to live somewhere else. And where it lives is right here. It lives 1 unit above 0 on, let's make another number line here. Cross 2 number lines, we get I is here. Actually, negative I would be there. 2I would be there, etc., etc. And those are the imaginary numbers. Real numbers here, imaginary numbers here, which is any real number times I. And when you add or subtract these together, you get something like 2 plus I would live right there, over to 2 on the real number line, up to I on the imaginary number line. 3 minus 2I would be down here. So a complex number is defined as any real number plus or minus any imaginary number. And it corresponds to a place in this thing that we call the complex plane, right? 2 plus I would be the same place you'd think of 2 comma 1 being as a point in the Cartesian coordinate system. 3 comma negative 2 would be here, so 3 minus 2 i's there. Okay, that's where these numbers come from. That's why we have them. We're going to be doing some things with them, but not as much as we could do. They're really a lot of fun when you get into them.